this video we are going to study about subspaces of a vector space. What is subspace? If I have a vector space V over a field F and W is my non-empty subset of V, then I can say W as a subspace of V if W itself is a vector space over F with respect to the same operation which is defined in V. I mean to say that if W is a non-empty subset of V and if W is a subgroup of V and for each alpha belongs to field F and vector W belongs to W, then alpha W belongs to W, then I can say that W is a subspace. In fact, it is very easy. If I have a subset W and I have to show that it is a subspace, for that I have to show it is closed under addition and scalar multiplication and it satisfies the axioms of vector space, then I can say that it is a subspace. First thing is it should be non-empty and I have to check for the closed nature under the addition and multiplication. So let me give a simple example. Suppose R2 is my vector space. Say I'm taking a vector space V, that is R2, and I'm taking a subset, say W, which is defined like this, which is a subset of R2 and any vector is defined like this, such that X belongs to R. Okay, this is a subspace. Because what does it implies? X comma 0, that means x-axis in the Cartesian plane when you consider R2. So any vector, this is non-empty of course, and if I take any two vectors from this set, I have to add up, I have to check for scalar, I have to add up, where I have to take up vector addition and scalar multiplication. So two vectors I'm considering, say x1 comma 0 that and x2 comma 0, they belongs to my set W. Okay, then if I add them, that gives me x1 plus x2 comma 0, which again belongs to W. And for any alpha belongs to the field F, if I consider, then any scalar alpha x1 comma 0 if I consider, this is same as writing alpha x1 comma 0, which is also belongs to W. Therefore I can say that this W is closed under addition and multiplication and it satisfies the vector axioms. Therefore W is a subspace. In fact, for any vector space V, always remember that if V is any vector space, then the null space and the vector space itself, they are the subspaces of V. Okay, and these are called actually trivial subspaces or improper subspaces. Trivial subspaces, or I can say improper subspaces. A vector space V itself and a null space, they are the subspaces of a vector space V and they are called improper subspaces or trivial subspace. And one more example I can give. This is one example and this is a note. One more example. If I have vector space V as a set of complex numbers, and if I take then set of real numbers, that is W. If I take W as set of real numbers over the field R, so over the field R, then W is a subspace of vector space C. And I can give you one more example. Suppose I have two sets here. Okay, I have a vector space V, which is R3 over real numbers. Okay, my vector space is this. Now I have two subsets, that is W1, which is x, y, z, any vector x, y, z, such that x plus y plus z equal to 1. And one more subset, which is x comma y comma z, such that x plus y plus z is equal to 0. Now among these two subsets, which is a subspace of V, which is a subspace of R3? I have to check. W1 is this. First thing, see, when you have to check whether the set is subspace or not, first I have to check whether it is non-empty or not, and then I have to check for addition of two vectors and the scalar multiplication. Okay, see, when I have defined W1, this has the vector x, y, z in such a way that x plus y plus z equal to 1, right? Now this is of course non-empty, no problem. Okay, there is element in this set, so W1 is non-empty. But see, I have to check. I can say W1 is a subspace if it itself is a vector space, right? To say a vector space, it should be an abelian group. When I say group, abelian group, then it should have an identity element. Over addition, when I consider, the identity element is 0, 0, right? Huh? But this belongs to W1? No. Why? Because any vector in W1 is of this kind. If I add up all the elements, the entry should be equal to 1. But when I consider the identity element, that just does not belongs to W1. Therefore, I can say that W1 is not a subspace. Okay. Don't simply go for adding two vectors and all. Have to check for the non-emptiness and then just think of it by looking at the condition they have mentioned in the set. Okay. Similarly, when I take the second set, that is W2, here the elements are such that x plus y plus z is equal to 0. Here no problem. The sum is 0. Of course, this is non-empty, right? It is non-empty, and you can check for the addition of the vectors and scalar multiplication. Since the sum has to be equal to 0, the entries are 0, 0, 0. Sum has to be equal to 0. So this is a subspace. W2 is a subspace. Similarly, you may get the questions like they'll give you set of some subsets and they'll mention you the vector space. You have to check whether it is a subspace or not. Say I'll take up one more example. Example 4. I have a vector space over real numbers n, and I have a subset W in that each vector is like this, is an n tuple, in such a way that sum of the entries similar to this, okay, sum of the entries which is equal to 0. Then I have to show that, I have to check in fact whether it is subspace or not. Of course, it is non-empty, so no problem with the emptiness. There is element in W. Now let two elements I'll consider, x and y. belongs to W. Then I have to check whether x plus y or x minus y belongs to W or not, and I have to check ax belongs to W or not. So if I consider x minus y, then what happens? Two vectors are x1, x2 dash dash xn minus y1, y2 dash dash yn. This is same as writing x1 minus y1 comma x2 minus y2 dash dash xn minus yn. I'm saying this belongs to W because see, how is any element in this? Their sum should be equal to 0. When I take these sums, x1 minus y1 plus x2 minus y2 dash dash up to xn minus yn, I can write it as x1 plus x2 dash dash up to xn minus y1 plus y2 dash dash yn, right? I know this is equal to 0 and this is equal to 0, so this is equal to 0. So their sum is equal to 0. Therefore, I can say that x minus y belongs to W. Similarly, I'll check for scalar multiplication. If I have any scalar a, then ax is same as writing a into vector x1, x2 dash dash xn, which is same as writing ax1 comma ax2 dash dash axn. Right, I'm saying this belongs to vector space W because what happens to the sum ax1, ax2 dash dash axn, which is same as writing a into x1 plus x2 dash dash xn, okay, which is nothing but a into 0, which is equal to 0. Therefore, the sum of these entries gives me 0, so the condition is satisfied. Therefore, ax is also in W. Therefore, I can say that W is a subspace of set of n tuples Rn. And I can give you one more example, say example 5. I have set X such that elements are n tuples only, x1, x2 dash dash xn, okay, in such a way that entry x1 is greater than x2, okay. Is this a subspace or not? I'm asking. In R, if I take in R3, what happens? How is any vector in R3? Simply, instead of taking n vectors, I just take triplet. Okay, so in R3, how is any vector? Like this, x1, x2, x3. This is any vector in R3. Okay, now I'm putting the condition that x1 is greater than x3. Okay, so in general, just think of it. Don't go for proving every time if it is asked whether it is a subspace or not. Okay, just think with an example. If you can prove, then that is also fine. This is the case only if it is not a subspace. Okay, if it is a subspace, then you have to prove it generally, in fact. So I'll take two vectors. Okay, one vector is 1, 0, 2. This is in R3, no problem, and the condition is true. X1 is greater than x2. I'm sorry. This problem is for n tuple. I'm taking in R3 and showing. Okay, and if I take one more example, one more vector, say 2, 1, 5. These two are my vectors. Now, when I take this minus this, I'll call this vector as v1 and this as vector v2. Okay, now v1 minus v2, you can take xy also, no problem. If I take this 1 comma 0 comma 2 minus 2 comma 1 comma 5. Okay, now what happens to this? 1 minus 2 is minus 1 minus 1 minus 3. Yeah, in this case I can say that this v1 minus v2 does not belongs to R3, because see this entry, x1 entry, is equal to x2 entry, right? Which is, see, minus 1 is equal to minus 1. Minus 1, this violates the condition that x1 should be greater than x2, right? So I can say that this does not belongs to R3. Therefore, I can say that this R3, which is x here, okay, therefore x is not a subspace. Okay, so similarly, if I take n tuple also, the same thing. You, in general, you take some values for these two and rest you write dash dash dash, and take any vector addition or multiple subtraction and show that it does not belongs to this x, therefore it is not a subspace. One more example you have to check for this subspace nature. Say, suppose I have set S is such that x is n tuple x1 comma x2 dash dash xn, okay, such that the first entry and the last entries are equal to 0. Okay, of course this is non-empty. First condition is non-emptiness. It's non-empty, no problem. And second condition, you take any two vectors in the set x, y in the set S, and check for x plus y, whether this belongs to S or not. Of course, in this case, it belongs to S. You operate it, you explain this, okay? Then A is any element from the field F. If you take, then check for AX, whether this belongs to S or not. Okay, in this case it belongs to S. Therefore, S is a subspace. Next is properties of a subspace. Suppose B is a vector space over the field F, and W alpha, which is a collection of all the subspaces of V. And if I take intersection of all the subspaces and I denote it as W, then this also forms a subspace. So let us see how. W is intersection of all the subspaces. This alpha just indicates the subspace, okay, index of the subspace I am considering. I have to show W is a subspace. So to show W is a subspace, I have to check whether it is empty or not. It should not be empty. And then I have to check for vector addition and scalar multiplication. So first thing is, I know 0 vector belongs to all this W alpha, for all alpha belongs to the index I. 0 vector means 0 vector is there in all the subspaces. Okay, therefore this 0 vector is also in the intersection of all these subspaces. Therefore, I can say that intersection of W alpha is non-empty. Okay, I can say W is non-empty. So first condition is true. Second thing is I'll take two vectors in W and I'll check for the vector addition and vector multiplication. Okay. Let me take two vectors, say V and V dash. Say it belongs to the subspace, say W alpha, and it is there in all the subspaces. Okay, for all alpha belongs to I. These two vectors are there in all subspaces. Since I know that W alpha is a subspace, vector V minus V dash belongs to W alpha, and for any scalar A belongs to F, AV belongs to W alpha. Since I know W alpha is a subspace, so vector addition and scalar multiplication is true. And this thing is true for all alpha belongs to I. This is true for all alpha belongs to I, since each W alpha is a subspace. So since this is true, V minus V dash belongs to all W alpha, I can say that V minus V dash belongs to W, and since AV belongs to all W alpha, I can say AV belongs to W also. Therefore, I can say that W is a subspace of V. Okay, this is, I'm taking intersection of all the subspaces. Now the thing is whether union of all the subspaces of a vector space V is a subspace or not. So let us check that. If V1, V2 are subspaces of V, then V1 union V2 need not be a subspace, and it can be a subspace if and only if one is contained in other, in the sense V1 is a subset of V2 or V2 is a subset of V1. To prove this, just take, I'll give you an example. Say let R2 be my vector space. Okay, and I'll take two subspaces of this R2. Say V1 is such that x comma y, x comma 0. Okay, so it belongs to R, and another set is 0 comma y. Okay, I know these two are the subspaces. So no problem. How is any element in V1? In fact, it is, if I take this axis Cartesian form, x comma 0 means all the entries along this line, right? Along this line. And y comma 0 when I consider, this means all the entries in this line, y-axis, in this on x-axis. So when I consider their union, means V1 union V2, it is like this, x comma 0 such that this belongs to R and union with 0 comma y, right? That belongs to R. If I take any scalars alpha beta belongs to F, then alpha of x comma 0, alpha into x comma 0 and beta into 0 comma y, which gives me alpha x comma 0 plus 0 comma beta y. In turn, it gives me alpha x comma beta y. Okay, means the entry is x comma y. But this does not belongs to V1 union V2. Because how is this entry when I consider this entries maybe here, maybe here, maybe here, maybe here. But that when I take V1 union V2, V1 union V2 means the entries must be on this line or in this line, right? But when I take the entries, when I add two vectors, I'm getting the entries, it may be here, 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 anywhere here, right? It need not be on this line only or on this line only. Therefore, I can say that V1 union V2 is not a subspace. Not a subspace. To prove the second part, that is V1 union V2 is a subspace only if V1 is a subset of V2 or V2 is a subset of V1. So suppose I take if V1 is a subset of V2 or V2 is a subset of V1, then what happens? What happens in this case? V1 union V2. If V1 is a subset of V2, then V1 union V2 is V2 only, or V1 union V2 is V1 only. Since V1 and V2 are subspaces, this union is also a subspace, right? If one is contained in the other, then their union becomes simply V1 or V2. Since V1, V2 are subspaces, their union is also subspace. This is if and only if condition, so I have to prove the other way. If this is the case, then what happens to V1 union V2? Converse part, let us assume that V1 union V2, I'm taking it as a set V, which is a subspace. It's a subspace. Okay. And I have to prove, I'll get the contradiction to the fact, this fact. Okay. I'm taking contrapositive of the statement. If V1 is not contained in V2 and V2 is not contained in V1. Okay, then there exist vectors say V belongs to V1, but that does not belongs to V2, and another vector say W that belongs to V2, but that does not belongs to V1. Okay, but the vector V plus W in vector V. Thus, any two vectors, say vector V is in V1 but not in V2, and vector W is in V2 but not in V1. Okay, and I'm taking any two vectors, and since it's a subspace, I take V plus W in V. But this vector V plus W does not belongs to V1 union V2. Do you agree? Which is a contradiction. Therefore, I can say that V1 union V2 is not a subspace. I hope you got the point. See, I'm taking V1 which is not contained in V2, means they don't have any vector in common. In the same manner in this, okay, I'm taking one particular vector which is in V1 but not in V2, and I'm taking another vector which is in V2 but not in V1. When I take any vector over here, okay, they belongs to V. But in general, by this definition, if I consider V plus W, they does not belongs to V1 union V2, which is a contradiction. Okay. Therefore, I am getting V1 union V2 is not a subspace.